All right, so let's talk a little bit about zeros, complex zeros, and factoring in general. So just a quick reminder, if you do zeros, and when you have a function in factored form, we have zeros of 3, 1, and negative 2 in this particular function. And don't forget negative 2, I don't know what that marking is, has a multiplicity of 2. So that one bounces while the other two pass through. So this one here bounces with a multiplicity of 2. Then there's the whole expanding. If you do imaginary numbers and expand them, you just have to FOIL them out. Now it's the difference of squares. You're welcome to look at it that way. I'll do that later, but right now I'll just show you that if you FOIL it out old-fashioned like, here's what you get. Now don't forget I squared is negative 1, and also when you deal with i's, 2ix minus 2ix, those cancel. These guys right here totally cancel with one another because they're just opposites. And then this negative 4i squared is like negative 4 times negative 1, which is positive 4, and that's the end result from combining those, knowing that I squared is negative 1. Then on the end here, we've got, let's see, factors of 5, radical 2i, and negative radical 2i, just in case you're forgetting those are the roots that go with the factors. But what we're here to do actually is to multiply all this out. I do mention this time I went ahead and looked at this as the difference of squares. X plus some number times x minus some number. You can write it as the first number squared times minus the second number squared. So I've done that here just to help us shorten up some of the work that goes with it. So you have to remember that format allows us to rewrite in a simpler format. X minus 5, now the stuff on the right, radical 2i quantity squared is just positive 2, because squaring a radical makes 2, and I squared is negative 1. So that makes that whole thing positive, and then we just FOIL out the rest for x cubed plus 2x minus 5x squared minus 10, all that, and then any like terms or rearranging you want to do would be good, so I've done that here. Next big chunk is, what about the, if I have these roots, these zeros, what I need to do, pardon my yawn, is then make factors out of it. So I've done that here. And don't forget your imaginary roots come in conjugate pairs. You've got double the fun. So if I FOIL out the first bunch there, no big deal. The second bunch I'm going to recognize as, I'm just going to FOIL out all together. Just be real careful about FOILing those out. You'll notice all the pairs there, and then look for all the I squareds and other things. I'm going to distribute down here in this little section here. These two pieces need to be distributed with that x, and so you'll see that in the next step coming up. So those getting distributed nicely. On the end, I went ahead and took care of 2 squared is 4 minus I squared, which would be like plus, minus, and negative 1, or plus 1. So simplifying all that down. Combining some like terms, your x's and ix's and so on, looking for things that cancel. Canceling ix's leaves you just with negative 2x, and negative 2x is negative 4x. Obviously 4 and 1 is 5. And then from there you can FOIL the rest of that out. Good, pardon my yawn's getting a little sleepy. If you FOIL the rest of that out, there's that polynomial fully expanded. 3b we're just going to leave. It's a bit more work than we need to get into, but this is the one we were able to do in class. Let me know if there's questions you have on that piece. If we deal with complex zeros and I give you a complex zero, then you'll know it's going to go through. If you do synthetic division, you're going to get a remainder of 0, but multiplying those out is not such an easy task. The first one's no big deal. 4 times 1 minus 2i makes 4 minus 8i, and then you add 0, no big deal. But for all the others, like 1 minus 2i times 4 minus 8i, got to FOIL it out, got to take your time. Be careful, and then notice the combining i's. And then 16i squared is actually the same thing as 16 times negative 1 for negative 16. And combining all those real numbers, 4 minus 16 is negative 12. And then when you take that final product and you add it to 17, you make sure you just add only the real numbers to real numbers and complex numbers to complex numbers. So that 17 is added to negative 12 only. And you see that result here. And then again, here's another FOIL. 5 minus 16i times 1 minus 2i. Carefully multiply it out. And then what you'll look for is combining some like terms, and then I squareds make negative 1s, so it changes the sign. And then you take that piece, rewrite it in there, add only real numbers, and we're back to our final FOIL. So here that takes off, and then once that FOIL is taken care of, like terms added, I squareds accounted for, then what I get is a negative 65, a remainder of 0. Now, with conjugate complex numbers, you have a conjugate pair. The second 1 plus 2i, as it works through in synthetic division, we mentioned in class, you're going to get real number results, and this is kind of the magic of the problem. As I multiply through 1 plus 2i times 4, 4 plus 8i is the first result, add down, the i's cancel, so it's just 4 plus 4. Do it again, 8 times 1 plus 2i is 8 plus 16i that you see right here. Add them together, the i's cancel, you just have 13. Multiply 13 through, get 13 plus 26i, cancels with all of it above, and here's a remainder of 0. So it will happen every time with these conjugate roots. You're going to have one that works through, you get 0 as a remainder after some pretty hard work, and then the second one, you'll go through and all the coefficients of the quotient will be positive numbers. That is a quadratic, so we can use quadratic formula to knock this one out, and I'm going to do that relatively quickly here. Good knowing you guys are pretty handy with good old quadratic formula. 2 imaginary roots accounted for over there, and that's the end of the story. So that gives you the idea of finding complex roots and expanding them and testing them using synthetic division. All the things we've done so far can be also done with complex numbers.